Hello, this is a video on inverse binomial sampling, and really it's a relationship between the negative binomial and a binomial random variable. So if we let x equal a negative binomial with parameters r and p, x goes from r to infinity, and we let w be a binomial random variable with parameters n and p, where w goes from 0 to n, then it follows that these two probabilities are equal. And this says that the probability that we observe our successes before n, or equal to n, is the same as that we observe at least r successes and n trials from a binomial random variable. And when you write these two summations or probabilities out, at first it absolutely does not look like they should be the same. And so to illustrate this in R, and when I was first proving this, I took a simple case, something that I could write out and drive those and, multiply out the polynomials and show that they're equal, and they are. And so and of course I do this in R to make sure that I'm thinking about it right. So I chose 7, N7, R5, and P equal 0.4. And then this is the CDF of a negative binomial in R. Now, this theorem is defined as x goes from R to infinity, but in R, the R software, it goes from, the negative binomial's domain is 0 to infinity. So you have to, redefine that probability a little bit. And that's what the n minus R is. And then this sum, of course, is the summing the binomial probabilities from R to n. And they do equal. And then to show it is true for something larger, so N50, R7, P equal 0.24, and then these two probabilities are equal again. Now what I want to do is prove this, and it's a little bit messy or detailed. I'm going to try to go through it as quickly as possible, but in enough detail that you could reproduce this and understand it on your own. So this is how I ended up proving this. First of all, I want to write down what we must show. And we must show that these two probabilities are equal. And if you write out the summation for a negative binomial, you get this. And if you write out the summation for a binomial, you get this. And if you look at these two summations and these two polynomials that you get, it doesn't look like they should be equal, but they absolutely are. Now, to show that these two summations are the same, I found it easier if we divide both of these sides by p to the r. So showing these two are equal is equivalent to showing this equal, dividing both sides by p to the r. And that's why this one goes away and this one is, I minus r. So we're going to use induction to prove it. So first let's let n equal r. And then when you plug in r for n everywhere, the left-hand side is 1 and the right-hand side is 1, and so they are equal. Now we assume it's true for r plus m, and then we have to show it true for n equal to r plus m plus 1. So we plug in n equal to r plus m plus 1, and that's what this expression is. And so this is the negative binomial, this piece here. That last term we separate out, so this is the sum from, take out the 1, otherwise it's the same, and this is that last term. Well, by the induction step, we assume that this is equal to this by the induction assumption. So we plug that here. And then, of course, this term just comes straight down. Now, by Pascal's triangle and a well-chosen 0, we get the next step. So this piece here is using Pascal's triangle, and the way you sum binomial coefficients, this is equal to this piece. Otherwise, everything comes down. This piece is here, and then we add this expression and then subtract it. And so this, we're adding 0. It's a well-chosen 0. Next, we start simplifying things. So separating the sums, so we multiply this into each of those and then make it two summations. And then we add another well-chosen zero. So these first two is that separating the sums is what I call it. And then every piece comes down, except for the p that was out here, we take it into that sum. That's what this +1 is on each of these. And then we add another well-chosen zero right here. Now, combining terms 1 and 5. Now, yeah, so this term and this term, and then because they're summed from r to r plus m, so we can combine them, and then we factor out everything, and it ends up that it looks very similar, but we just get an extra +1 in the 1 minus p. So this term is combining terms 1 and 5 from before, and otherwise everything comes down, and then this well-chosen zero. Now combining terms 1 and 5, so 1, 2, 3, 4, 5, so the first term and this term. Now if we go from +1, this term is this when we add one more term, so we can take that into the sum and notice the +1. So this expression is terms 1 and 5 in this first one. This comes down, this piece is here. This term, we separate the binomial coefficient. We use Pascal's triangle again and separate those. Otherwise, it comes down. That was added in the term 1. This one comes down. Now here we add term 2 in the second part of term 4. So we add this term and this term. So when we multiply these in, this second term gets combined with this. And notice that it ends up being just an extra +1 in the 1 minus p when you do that math. So this term comes down, this, term 2 and the second part of term 4 combined to this. Otherwise, and then of course this comes down, we have the minus p. Now combining 2 and 5, so 1, 2, 3, 4, 5, so combining these two, and 3 and 4. So this first term just comes down, and then 2 and 5 become this here. Notice the extra +1. That's what this term is. And then these two, this one actually gets taken into the initial state. So it's I equal r minus 1. So that's this. Well, this here, if we re-index it, so re-index it j equal I minus 1, then this term becomes this. So it's indexed at j. So the first term comes here, this last term is here. But the index is really just a dummy variable, right? So here we're subtracting and then adding the same quantity. So we're left with just this term. And thus the results follows, because that's what we wanted to show. And so the theorem is proven. And so let's go back to the top. And so thus this theorem is true. And this is often referred to as inverse binomial sampling. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.